There's a particular family of integrals that comes up in applications that students tend to shy away from. I want to introduce those. So one natural context where these come up is the context of finding the length along a curve. And related contexts would be surface area, mass, energy. These calculations could come up in finance. They could come up for various other settings. It's an important class of integrals. The thing that students shy away from is the fact that you have to know a little bit of trigonometry. But trigonometry is a really powerful tool for describing various phenomena in science, and you really don't want to hide from trigonometry. So it's good to get a little practice with it here and there. For this particular problem, I want to look at y equals x squared, and I want to look at the length along this parabola from x equals 0 out to, let's say x equals a, where a is some positive constant. The arc length comes from integrating the length element. The length element you can get using the Pythagorean theorem on a right triangle that has change in x, a length of change in x in the x direction and change in y in the y direction. You can do a little algebra. There are other ways to get to this result, but what you end up with is the integral of the square root of 1 plus the derivative of the function squared. And so for this particular example, I'm going from x equals 0 to x equals a, and my derivative is 2x. So when I square it, I have 1 plus 4x squared dx. Another similar type of example is where this is not a plus but a minus. And we can handle both of these. It's a little faster to handle the negative form of this family, so I'm actually going to switch to that for the purposes of keeping your attention for the length of this video. So this calculates something different than length, but you can see obviously this expression is related to this one. So I'm going to switch over to here. In both cases, what we're going to do is get rid of the square root by using a trigonometric equation, and we're going to go back to the trig identities that come from the Pythagorean theorem. So they're called Pythagorean identities. You probably remember cosine squared plus sine squared equals 1. And then there's a similar one that involves tangent squared and secant squared. I'll write those over here. If I divide both sides of this equation by cosine squared, then this first term turns into tangent squared. Cosine squared turns into 1. And on the right I get secant squared. And it's probably better if I use the variable of theta, or just something besides x, since I have x's in my original problem. So I'll think of these as thetas instead of x. All right. Notice here, 1 plus 4x squared is kind of this form, 1 plus tangent squared. So if I let tangent squared theta equal 4x squared, then I can replace this with the square root of 1 plus tangent squared theta. which would make it the square root of secant squared theta from this equation. Square root of secant squared is just secant, so square root is gone. Then you just have to figure out how to rewrite dx in terms of d theta. For this problem, instead of using the tangent squared plus 1 equation, I'm going to move either sine squared or cosine squared over to the other side. So for example, if I subtract sine squared, then I get cosine squared theta equals 1 minus sine squared theta. That's what I use here. So what I'm wanting to get to is the square root of 1 minus, what did I say, sine squared theta. And then this dx, I'm not sure what that's equal to in terms of d theta, but I can figure it out. So what I did to get to here was I said for x, I'm choosing for x to be equal to sine theta. And so I can say exactly what x is in terms of theta. Divide both sides by 4. Now I can take the derivative of both sides with respect to theta, or take the derivative of x with respect to theta. And I'll solve for dx by multiplying both sides by d theta. So then I can replace dx with 1/4 cosine theta d theta. I'll write it like this. Cosine theta d theta over 4. And I'll leave the bounds as x equals 0 and x equals a for now. All right, so then the 1 minus sine squared again turns into cosine squared. The square root of cosine squared is cosine theta. The cosine theta multiplied by this part gives me cosine squared over 4. And then I'm going to leave my bounds alone for now. I'll come back to those later. Now I want to integrate cosine squared over 4. I'm almost done. Cosine squared, I can't get that directly, but there is a nice equation for reducing the power on cosine squared. If you remember, cosine squared can be rewritten as 1/2 times 1 plus cosine 2 theta. So I'll bring that 1/4 out, and then just the cosine squared turns into 1/2 1 plus cosine 2 theta. I'm not just randomly pulling this out of thin air. This comes from writing out what cosine of 2 theta is using the angle sum formula. So you need to know these two equations, these Pythagorean identities, and then you also need to be able to reduce cosine squared and sine squared. You can just look up power reduction formulas for cosine and sine to remind yourself of what those are. Now the 1/8 will pull out in front. Antiderivative of 1 is theta. Antiderivative of cosine 2 theta is something like sine 2 theta, but I have to make an adjustment because the derivative of sine 2 theta is cosine 2 theta times the derivative of 2 theta. I have to use the chain rule. So to balance out that extra 2, I have to use a 1/2 for the antiderivative. So now the derivative of 1/2 sine 2 theta is 1/2 cosine 2 theta times 2, which is just cosine 2 theta, so that works. I could have used a quick u substitution to write this out as well, that's fine. Now, I basically just need to go back and rewrite what theta is in terms of x, what sine of 2 theta is, and then I can plug in my bounds. So instead of having a plus c there, I'll remind myself that I had x equals 0 and x equals a. And I've got options for how to finish this up. Theta, to get theta in terms of x, I can take arc sine on both sides. And then for sine of 2 theta, what I want to do for that is use another trig identity. So the angle sum formula for cosine leads to the equation that we got here. There's another one for sine, and it says it leads to the equation sine 2 theta equals 2 times cosine theta times sine theta. So altogether I get theta plus sine theta cosine theta. Now sine theta is 4x, cosine theta is what we ended up with here. We had the square root of cosine squared, which is just cosine. So this square root is what cosine will be equal to. We could also set up a triangle using this trig ratio, sine theta equals 4x over 1. You could set up a triangle and solve for cosine on that triangle. Theta is arc sine of 4x. Sine theta is 4x. Cosine theta is that square root that we started out with. All right, and now we can just plug in our bounds as usual, and we get a nice answer, a final answer from this. It's a little complex. Remember, what we started out with was the length of a parabola. This is not that problem because I changed the plus to a minus, but it's related to that. So the hurdles that get in students' way are the trig identities. So please don't be intimidated by the trig identities. Those are things that you can get down if you don't remember them. You can get back to them fairly quickly. And then just the length of the problem, which I can understand. But if you're working out like calculus homework, and this is kind of a pain to have something this long. But if we're talking about a project, a meaningful project where you're making an important calculation for something really fun that you're doing, or for something important for work, then this is actually not long at all. It's a very minor problem when you think of the kind of applications that you're going to be working on in the future.